Okay, so hi everybody, welcome back. Today we're going to be starting a new chapter. That's chapter 35 of Giancoli. And there are a number of different topics covered here, but a couple that I wanted to highlight in particular in this lecture are diffraction and polarization of light. So let's get into this. And so we'll start with diffraction. I'm going to introduce this idea to you, get the concept down, and then also we'll introduce some equations that describe diffraction in the simplest case. And then after this, we'll move on to some more complex cases of diffraction. So let's start with the definition. What is diffraction? Well, diffraction is when a wave bends around an obstacle or spreads out after going through an opening. So let me give you a few examples here to illustrate the idea. So in these two examples, we have Alice and Bob. And Alice is going to call out to Bob. She's going to emit a sound wave, and hopefully Bob will be able to hear it, okay? So in the first case, Bob is hiding behind a tree. In other words, the line of sight between Alice and Bob is completely blocked. There's no way that a sound wave could go from Alice to Bob if it's just moving in a straight line. But here's the thing, in this situation, as you may know from experience, Bob will be able to hear Alice. Okay, so what's happening? The sound waves that are emitted by Alice are actually bending around this obstacle. They're bending around the tree, and they actually do reach Bob. So Bob is able to hear Alice because of diffraction, because we say the sound waves diffract around the tree. They bend around that obstacle. So here's another example. Instead of an obstacle, we have an opening. So imagine we have a wall with a small doorway in the wall. So Bob is hiding behind the wall, and again, there's no line of sight between Alice and Bob that isn't blocked by the wall, so there's no way for a sound wave to just move in a straight line and get from Alice to Bob. But again, nonetheless, Bob is able to hear Alice because the sound waves diffract after going through the doorway. They bend after going through that opening. Okay, so both of these are examples of diffraction. So one really powerful tool that we have to visualize how diffraction works is something called the Huygens Principle. So back in the late 1600s, there was a Dutch physicist named Christian Huygens, and he came up with a method to analyze how waves propagate through space, how they move. So here's how it goes. Every point on a wavefront may be considered a source of secondary spherical wavelets, which spread out in the direction of the wave at the same speed as the wave. The new wavefront is the tangent to all of these secondary wavelets. Okay, so the best way to understand what this is saying is to look at an example. So let's try to apply Huygens' principle to this curved wavefront. In other words, we know that this is one of the wavefronts. We're going to use this to predict what the next wavefront looks like as the wave moves forward. So each point on this wavefront is going to be considered a source of secondary spherical wavelets, which spread out in the forward direction like this. So we're going to show the wavefront with a solid line. These secondary wavelets are going to be shown with a dashed line. And the arrows are showing us which way the wave is moving. So here's one spherical wavelet going out. Here's another one at this point. Here's another one at this point, and so on. We could draw as many of these as we like, but we can already see what's happening with just 3. So the next wavefront is going to be the tangent to all of those. So that would be this solid line here. This would be our next wavefront. Okay? And then we can do this all over again. Okay, we can say at this point on the wavefront, we can consider this to be a source of a spherical wave moving forward. This point, again, we can think of that as a source of a spherical wave moving forward, and this point as well. And then the tangent to all of these wavefronts is the next wavefront. Okay, so we can predict how the wave moves just by applying Huygens' principle to the waves, and you can probably guess how it goes after this. We don't have to continue, drawing these spherical wavefronts. We know that the pattern emerging is we just get more and more curved wavefronts moving outwards. So let's take a look at another example where we can apply Huygens Principle. In this case, we have a plane wave. So the original wavefront is shown here. This is an infinite plane, but we're just looking at it from the side. So we're seeing the plane edge on, okay? Now, just like before, every single point on that plane can be considered a source of a spherical wave, which is moving in the direction of our wave. So just moving to the right in this case. And we can do this for all the points on the wavefront. And what we can see is the tangent to all of these spherical wavefronts is just another plane. So the next wavefront that we draw is just another plane identical to the first one. And then we can play the same game again, where we take points on that plane and we show them as sources of spherical wavefronts moving forward. And that gives us the next wavefront tangent to all of those, which is another plane. And so if you do it again, same thing happens. We get another plane. So the takeaway here is if you start with a plane wave, all subsequent wavefronts are also going to be planes. They're going to be infinite planes parallel to the first. So when you have a plane wave, the situation is pretty simple. You just get more plane waves moving forward. So let's tweak that previous example just a little bit by having the waves go through a narrow opening. Okay, so here is the narrow opening. We have coherent waves that are approaching it. And of course, they're going to be plane waves just before hitting that opening, but what about afterwards? So let's take a look. We have a plane wavefront shown here, just about to go through the opening. If we want to predict what happens next, we can use Huygens Principle. So at each point along that wavefront, we show a spherical secondary wavefront going outwards, and the next wavefront is going to be the tangent to all of these. So we can draw that, which, if you notice, is no longer just a straight line. It's curved at the edges. That's really important. And then we can do it again to see what the next wavefront looks like. Again, each point along this new wavefront is going to be a source of spherical wavelets going out in all directions. And of course, we can draw the tangent to all of those. It's going to be another curved wavefront like this. And then we can do it again. This time, I'm not even going to show the secondary wavefronts. You can kind of see the pattern that's emerging. We get another curved wavefront coming out, and another one like this. So what you might have expected to happen is that the wave sort of just gets cut off at the sides, and so it just moves in a beam which ends here and ends here on this side, right? But instead, what's happening is the waves are spreading out around the opening. That's diffraction. The outgoing waves are bending around that opening. That's what diffraction is all about. And so that takes us to single-slit diffraction. Here's the basic setup. We have two screens. One of them is our slit screen, which just has a single narrow slit opening on the screen. Okay, so light can go through that narrow slit, and then after going out of the narrow slit, we can project that light onto the viewing screen over here. That's the basic idea. Now, in order for this to work, the light has to be coherent. So the easiest way to do this is to use a laser as your source. That will produce coherent light waves. And so here are the light waves approaching the slit. What we want to do is predict what will happen after the light waves go through the slit. And of course, we can use Huygens Principle to get a visual picture of how that works. But what I want to do is develop some equations that describe exactly what we're going to see, what pattern of light are we going to see on the viewing screen. Okay, so we want to go from just a visual picture to some mathematical equations. But again, Huygens Principle states that at the slit screen, we can consider each point on the slit to be a source of spherical waves moving away from the slit. So let's show that for this point over here. We have spherical wavefronts moving away from that point. Let's do it again over here. We have spherical wavefronts moving away from that point. And technically, we could divide this slit into an infinite number of points. I'm just showing you 4 of them. But it gets the basic idea across. that what we have are different sources of waves. Depending on where we are on the screen, those different waves can interfere, sometimes constructively and other times destructively, okay? That produces a pattern of light on the screen, which we call our diffraction pattern. And it looks in a lot of ways to be similar to the double slit interference pattern from the previous chapter, but there are some differences when you actually look at the details. So we have a very bright spot at the center of the pattern with a dark spot next to that, followed by a bright spot, followed by another dark spot, and so on. And that pattern of alternating bright and dark spots continues on the screen, and that's our diffraction pattern. And again, all of this can be understood in terms of constructive and destructive interference of all of these outgoing light waves emerging from the slit, okay? So I'd like to show you an actual single slit diffraction experiment. So here we have a track, and on the very left side of the track is a laser. The wavelength of this laser is about 635 nanometers, so it's emitting red light. That light is going through a single slit, which is over here. This is our slit screen. The slit is actually so narrow that it's probably too small to even see on video here, but the width of the slit is about 1/100th of a millimeter. So the light goes through that very narrow slit and then gets projected onto the piece of paper over here. Now, since the room lights are on, it's a little bit hard to see the diffraction pattern. So next, I'm going to cut down the room lights so you can see that diffraction pattern a little bit more closely. So now this is what the diffraction pattern looks like when we cut all of the lights in the room off. So you can see a very bright spot at the very center of the pattern. On either side of that, you have a series of dark and bright spots, which are alternating. And this is the pattern that I showed you in the lecture. This is what you get when you send a laser beam through a very narrow slit. So I'm going to start by just giving you an equation. We're actually going to derive this later in the lecture, but for now, I want to take a look at that equation and just try to understand what it's saying. So here's the basic setup. Here are some of the parameters that are going into the equation. We have our slit screen, of course, and the width of that slit is going to be denoted by A. So A is the width of the slit from one end to the other. Then we have a center line, which goes straight from the middle of the slit to our viewing screen like this. And the distance between the slit screen and the viewing screen is going to be L. Okay, just like before, this is going to be denoted by L. Now, we can locate points on the viewing screen by either giving an angle. So theta is the angle relative to that center line, which takes you to a certain point on the screen. But we also have y, which is a distance from the center line to a certain point on the screen, okay? So again, we can specify a position by giving a distance or an angle. Now, here's the equation that I'm going to give you now that we'll derive later. The diffraction minima, which are the dark spots or the dark fringes on the screen, these are the points where we have destructive interference occurring. These points of destructive interference are going to be located at A sine theta is equal to m times lambda. Okay, so these are the destructive interference or diffraction minima points. Now, m, as before, is an integer, but we have to be careful with how we specify this integer. M can be 1, 2, 3, or any integer after that, but m equals 0 does not work. In other words, if you plug in m equals 0, that does not give you a point of destructive interference on the screen. It just doesn't work that way. And so this equation that we were just introduced to describes the single slit diffraction pattern. In other words, the pattern of bright and dark spots that we see projected onto the screen. Now, this tells us only the location of the minima. That would be the dark spots where the intensity is at a minimum. So in the very center of the pattern, we see a bright spot. Right next to that, on either side, we have a dark spot, which is the m equals 1 minimum. Then we have another bright spot, and then another dark spot, which is the m equals 2 minimum, and then again, another bright spot. this dark spot over here is the m equals 3 minimum. So that pattern just keeps going as we go on either side of that central bright spot. And also the maxima, which would be the centers of the bright spots on the screen, these are approximately located halfway in between the adjacent minima. So here's what I mean by that. If this is the m equals 1 minimum, and this is the m equals 2 minimum, the center of this bright spot in the middle of those two minima is approximately at the halfway point between them. Okay, so the center of that bright spot is about halfway between the adjacent minima. So one thing we might want to know about this diffraction pattern is how wide is that central bright spot? And so let's call that W, the width of the central bright spot on the screen. Now, one thing that we're going to see later on is that most of the light energy is contained in that central spot. And these other spots are very dim and they have very little energy compared to that central bright spot. So sometimes we want to know how wide is that central bright spot. So as long as angles are small, we can approximate the width of that central maximum on the screen to be W is approximately equal to 2L times lambda divided by A. Now, I'm going to derive that equation for you in a second, but let's actually just take a look at it and see what it's telling us. So W is inversely proportional to A. W is the width of that bright spot on the screen. A is the width of the slit that the light is going through. So this is telling us that the narrower the slit is, the wider the diffraction pattern will be. And then if we have a wider slit, the narrower the diffraction pattern will be, because again, W and A are inversely proportional to one another. Okay, so let's start by drawing a picture. Here is our slit screen. The width of that slit is A. And then over here we have the viewing screen. Let's draw the center line between those two screens like so. The distance from one screen to the other is going to be L. Okay. Next, we're going to draw the diffraction pattern that appears on our viewing screen. We have a central bright spot, which I'll show right here. And then we have a bright spot next to that, but there's a little dark gap in between them. That little gap in between is the m equals 1 minimum. And of course, we have 1 on either side. The pattern is symmetric. Now, the size of that bright spot, which we'll call W, specifically we're talking about the width of the central maximum. Okay, so one result that we have is the dark spots, that is the minima, are located at A sine theta equals m times lambda, where m is an integer starting from 1, 2, 3, and so on, okay? So if I draw the angle that takes us to the m equals 1 minimum, let's call that theta right here, that helps us form a right triangle on our diagram, okay? So we have a right triangle, and the tangent of the angle theta that I just drew is equal to the opposite side over the adjacent side in that triangle. Okay, well the opposite side is not the width, but half of that, so W over 2. The adjacent side is L. Okay? But we're going to assume small angles. And one thing that we saw in the previous lecture is that for small angles, tangent theta and sine theta are approximately the same thing, which is useful, because if we go to our equation for the diffraction minima, there's a sine theta in there. But if we have small angles, I can replace that with tangent theta, which is equal to this, W over 2L. So I have A times sine theta, which I'm going to approximate as W over 2L, equaling M times lambda, but specifically, we're talking about M equals 1 here. So plug in 1 for M times lambda, and then solve for W. And actually, I should be careful here. This is not exactly equal. This is an approximation, so that's an approximation, which gives us W is approximately equal to 2L times lambda divided by A. Again, only valid for small angles. That's where this came from. Okay, so let's take a look at an example. Here we have a laser beam with a wavelength of 750 nanometers passing through a slit that is 1.0 times 10 to the minus 3 millimeters wide. So it's a very tiny little slit. The diffraction pattern is projected onto a screen that is 0.20 meters away. What is the width of the central maximum? We're going to give the answer as an angle in degrees and as a length in centimeters. Okay, so we want to know how wide is that central spot on our diffraction pattern, both in degrees and in centimeters. So let's work it out. Okay, so the first thing to go over here is the fact that the width of the diffraction pattern is inversely proportional to the width of the slit. Now here we have a very narrow slit, which means we're going to have a very wide diffraction pattern. So for that reason, we might not be able to use the small angle approximation. Given that we have a very wide pattern, is it true that we're going to be dealing with small angles? Well, let's actually answer that question. If this is our slit, the width is A over here, and this is our viewing screen, and here's the central bright spot on the viewing screen, where the width is W. L over here is the distance between the two screens. And here's the center line. Well, basically, if I draw a line going from the center of the slit to this edge of the central bright spot, and then another one going to the opposite edge like this, I'll see that I have an angle theta relative to the center line. There's also the full angle, which I'll call alpha, okay? So the question is, can we assume small angles? Well, the easiest way to answer that question is just to calculate an angle. So we have A sine theta equals M lambda, where M is 1, 2, 3, and so on. These are the minima, okay? These are the points of minimum intensity where you have a dark spot. So if we plug in M equals 1, we have A sine theta equals 1 times lambda, or sine theta equals lambda over A. So theta would be the inverse sine of that, inverse sine of lambda over A. And that would equal the inverse sine of, okay, lambda, 750 nanometers, that's 750 times 10 to the minus 9 meters. Then we have A, which is 1.01 times 10 to the minus 3 millimeters, but a millimeter is 10 to the minus 3 meters. So we have another 10 to the minus 3 coming into that. So if you actually work this out, it comes out to about 48.6 degrees. So actually, that is not a small angle. Small angles do not apply. Okay, so we're not using the small angle approximation here. But now that we have that answer, we can calculate alpha, which is how wide is the central bright spot in terms of an angle, alpha is just 2 times theta, right? It's going off the diagram. So that would be 2 times 48.6 degrees with 2 sig figs, by the way, which would be 97.2 degrees. Round that to a nice 97 degrees with 2 sig figs. Okay, so it's a very wide pattern, as we said earlier. Now, the next thing we can do if I want to actually solve for W is just like before. Let me just actually shade it in right here. We have a nice right triangle shown in red. And that right triangle can be analyzed in terms of the tangent function. Tangent theta is equal to the opposite side over the adjacent side, which is W over 2. Okay, that's this side right here, divided by L. So if we want to solve for W, that's going to be 2 times L times tangent theta. So we have 2 times L, which is 0.2 meters, times tangent theta, which is 48.6 degrees. Now this works out to 0.453 meters. Keeping 2 sig figs and then converting to centimeters, that's about 45 centimeters. So that's how wide that central spot will be on the screen. So here's one for you guys to try to work on. We have a laser beam with a wavelength of 535 nanometers, which passes through a slit that is 0.0150 millimeters wide. The resulting diffraction pattern is projected onto a screen, which is 1.20 meters away. The question is, how far is the first off-center maximum from the central maximum? In other words, here's the central maximum at the very center of the screen. The first off-center maximum is the one right next to that. We just want to know how far apart are these two. So we're going to give the answer as an angle in degrees and also as a length in centimeters. So pause the video, see if you can work this out, and then we'll go through it together. Okay, so we'll start by drawing a picture. Here is the slit screen. The width of the slit is A. And then over here we have the viewing screen. Let's draw the center line between the two screens like this. And the distance between them is L. Okay, so next, let's draw the diffraction pattern that appears on the viewing screen. We have a central bright spot, and then a gap, and then another bright spot off the center line over here, and another one over here. So these are the first off-center maxima on either side of the central one. And the pattern is completely symmetric, okay? So what we're trying to find is this distance right here, which we'll call x, but also this angle here, which we'll call theta. Now, to understand how to find the angle theta, let's call it theta max because it takes us to the maximum. We have to understand that that maximum is exactly halfway in between two minima. So here is the m equals 1 minimum, and on the other side is the m equals 2 minimum. Now, the locations in general of the minima are given by a sine theta. Let's call it theta min to be precise. Equals m times lambda, where m is equal to 1, 2, 3, and so on. Okay. Now remember, if we're interested in the maxima of intensity are located halfway between the adjacent minima. So here's the idea. We want the maximum that is in between the m equals 1 and m equals 2 minima, right? We're looking for the maximum right here, in between m equals 1 and m equals 2 minima. So the way we could do this is we could simply use a half integer, 1.5 or 3/2 for m. And so we have a sine, now we have theta max equals 3/2 times lambda. That's what we're plugging in for m in our original equation over here. So we have sine of theta max equals 3 times lambda over 2 times a, and then we'll take the inverse sine of that. So the inverse sine of 3 times lambda over 2 times a to get theta max. So this works out to the inverse sine of 3, lambda is 535 nanometers, so 535 times 10 to the minus 9 meters over 2 times a. A is 0.0150 millimeters, so that would be times 10 to the minus 3 meters. Now this works out to 3.067 degrees. With 3 sig figs, that's about 3.07 degrees. So back to the picture, that's our theta max. That's the angle we have to go off the center line to get to the first off-center maximum. Okay, next, let's figure out the distance x. Well, we have a right triangle where if we apply the tangent function, tangent theta max is equal to the opposite side, which is x, over the adjacent side, which is L. So that would be x over L. We want x, that's L tangent theta max. So plug in 1.20 meters for L times tangent of 3.067 degrees for theta max. This works out to 0.06429 meters with 3 sig figs, or 6.43 centimeters. Okay, so here's another example dealing with diffraction. This one is a little bit more conceptual. So we have a laser beam which goes through a rectangular opening that is narrower in the vertical direction than it is in the horizontal direction. So here's the vertical size of the opening, here's the horizontal size. It's bigger in the horizontal direction. That's the idea. So would you expect the resulting diffraction pattern to be more spread out in the vertical direction or in the horizontal direction? So take a minute to think this through, pause the video, see what you get, and then come back to it. Okay, so this is a picture of the opening that the laser beam is going through. Let's label some distances on it. Here is A vert. That's the size of the opening in the vertical direction. And here's A horizontal, the size of the opening in the horizontal direction. And we can see just by looking that A horizontal is bigger than A vertical. Next, we'll remember that the width of the central maximum, that's the central bright spot, in the diffraction pattern, okay, as long as we have small angles, is given by W is approximately equal to 2L times lambda divided by A. And the important thing to notice here is that W is inversely proportional to A. So the narrower the slit is, the wider the diffraction pattern is going to be. So we can see that W vertical is going to be greater than W horizontal. Okay, because if the slit is narrower in the vertical direction, then the diffraction pattern is going to be wider in the vertical direction. So the diffraction pattern is wider vertically. Compared to horizontally. Okay, so we've talked at some length about diffraction through a slit. So next, let's move on to a closely related problem, which is diffraction around a barrier. So here's the idea. We have coherent waves, which are approaching a barrier. The barrier is shown here. So our wavefronts are just planes before we reach the barrier. But once the wave hits the barrier, this part of the wavefront is going to get cut off. It will be absorbed by the barrier, but this part of the wavefront will remain, and this part on the other side will also remain. So if we want to predict how the wave moves past the barrier, we can use Huygens Principle. So at each point along the last wavefront that I drew, we can draw spherical wavelets, again, one at each point, and the tangent to those spherical wavelets will be our next wavefront. So we have one here on this side, and then another one here on this side. And notice something that's happening. These wavefronts are starting to bend around the barrier. So we'll do the same thing to this wavefront. We'll draw spherical wavelets at each point along the wavefront, and then do the same on the other side. And then again, the next wavefront is tangent to all of those. So one here and one here. And the overall pattern, again, can be extrapolated. So the next wavefront looks like this, and the next one looks like this. So again, what's happening is the outgoing waves are bending around the barrier. That's diffraction. And notice how at the very center, we have constructive interference. Okay, so this wavefront is constructively interfering with this one at the very center. You might expect that right in the middle of the barrier that you will see no outgoing waves because they would be blocked by the barrier. But the opposite is actually true. You get a very intense wave due to the constructive interference right at the center, where you'd expect there to be nothing at all. And so, of course, we're going to want to know what sort of equations govern diffraction around a barrier. How can I calculate what the diffraction pattern looks like when I have light going around a barrier as opposed to through a slit? Well, to answer that question, we have Huygens Principle of complementary screens. This says that the diffraction pattern produced by a wave going through an opening is identical to the diffraction pattern produced by a wave going around a barrier with the same shape. So let's take a look at an example. So here's an opening. It's shaped like a triangle. So we take a screen and we cut a little triangle out of it. Let's call this screen SA. Now, I could have a barrier that has the same exact shape. Instead of an opening in the shape of a triangle, it's a barrier in the shape of a triangle. We'll call that screen SB. Huygens' principle of complementary screens says that SA and SB produce the same diffraction pattern. So if I were to shine a laser through this opening or shine the same laser light around this barrier, I would actually end up getting the same exact diffraction pattern. Okay? So in other words, we can take what we know about diffraction through an opening and then just apply it to diffraction around a barrier and get the same result. So I'd like to take a minute here to talk about some of the history behind diffraction, and in particular, to tell you about a very famous experiment that was done that sort of solidified our understanding of how diffraction works. So back in the early 1800s, there were a lot of different French scientists who were working on this problem of diffraction. And in particular, there was someone named Fresnel who was coming up with a theory of diffraction using waves. So he thought that light was a wave, and he thought he could understand how diffraction works by thinking of light as a wave. So in 1819, he presented his theory to the French Academy. And there was someone there in the audience by the name of Poisson who was listening to this talk. and thought that there was something wrong about Fresnel's theory. He thought it implied something that was absurd. So the idea was, if you were to take a coin and then shine a light on it, of course, the coin will cause a shadow to be cast. But according to Fresnel's theory, at the very center of that shadow, there should be a bright spot, okay? In other words, there's a shadow and then a bright spot at the very center of that shadow. Poisson thought that that was absurd and it had to be wrong. But there was a third person in the audience named Arago who said, well, let me actually try that experiment out and let's see if it actually works that way. So he took a coherent light source and then shined that light source on a coin and then just projected that onto a wall. And he found, very surprisingly, that yes, you do get a very bright spot at the very center of the shadow cast by the coin. And in addition to that, you get this diffraction pattern all around the coin. And so with this idea of diffraction around a barrier in mind, let's take a look at an example. Radio waves and visible light waves are two different types of electromagnetic radiation. Radio waves have wavelengths of a few meters to several hundred meters, while visible light has wavelengths in the range of about 400 to 700 nanometers. So again, they're both electromagnetic waves, they just have very different wavelengths. So when a radio transmitter is behind a hill, you can still receive radio waves from it, even though you can't see it. So in other words, there is a hill, a radio transmitter, and then you are on the other side of that hill. So your line of sight to the radio transmitter is blocked by the hill, okay? So the idea is visible light from the radio transmitter is not able to get to you. That's why you can't see it. But the radio waves that it's emitting are getting to you. So how is that actually possible? How is it you're receiving the radio waves, but you're not receiving the visible light? So pause the video for a second, think this through, see if you can come up with an answer, and then we'll talk about it together. Okay, so the hill is a barrier, and we'll call the width of that barrier A. Now, according to Babinet's principle, this barrier will produce the same diffraction pattern as a slit of width A. So it doesn't matter if we're dealing with a barrier of width A or a slit with that same width, we'll get the same diffraction pattern at the end of the day. So the question we want to answer is, how much are the waves going to spread out after going around that barrier? Well, this is the hill. Let's draw the center line right here. We know that since we have diffraction, the outgoing waves will spread out. Now let's actually draw the central maximum. Okay, so this is the central spot of maximum intensity. On either side of that, we're going to have the m equals 1 minimum. Okay, so the angle that takes us from the center line to the n equals 1 minimum, we'll call that theta. But then the whole angle that takes us from one side of the central max to the other, we'll call that alpha. Now, alpha is just equal to 2 times theta, and this is the width of the central max. So if alpha is very large, it means we have a very wide central maximum. If alpha is small, we have a very narrow central maximum. That's the idea. Okay, well, remember that A sine theta is equal to m times lambda. For m equals 1, 2, 3, and so on. This is the location of the minima, if you remember. So we have a sine theta is equal to 1 times lambda if we want the m equals 1 minimum, which would give us sine theta is equal to lambda over a, or theta is equal to inverse sine of lambda over a, which means alpha is 2 times that, 2 times the inverse sine of lambda over a. Now, when it comes to visible light, again, wavelengths are on the order of hundreds of nanometers, but the size of the hill here, A, is probably going to be a couple hundred meters. So for visible light, lambda is much, much less than A. The wavelength is much, much less than the size of the hill, which, if you look at the equation we just wrote down, this means that alpha is very small. On the other hand, for radio waves, lambda is going to be on the same order of magnitude as A. In other words, the wavelengths are a couple hundred meters. The size of the hill is comparable to that, also a couple hundred meters. So alpha is going to be 2 times sine inverse of lambda over A, but those are pretty similar numbers, so this will be about 1, approximately. So 2 times the inverse sine of 1 is 2 times 90, about 180. Okay, so here's the takeaway. For visible light, the outgoing waves barely spread out around the hill. For radio waves, the outgoing waves spread out a lot. Which is why you actually can receive the radio waves on the other side of the hill, but you're not going to be receiving any visible light waves on the other side of the hill because the wavelength actually matters here. Okay, so what we want to do next is figure out how to describe a diffraction pattern in even more detail. We don't want to just be able to say there's a maximum here and a minimum there. We also want to be able to calculate the intensity of the light at different points in the diffraction pattern. So in order to be able to get there, we first need to develop a tool called a Phasor diagram. Okay, so that's what we'll talk about in this section, is Phasor diagrams. So fundamentally, a Phasor diagram is a visual aid. It's a tool that we use to visualize how a sinusoidal function behaves. So for example, let's say we have the function f of t is equal to a times cosine omega t. A and omega are both constants, t is the time. So we represent this function using an arrow, and the length of that arrow corresponds to the amplitude. So the longer the arrow we draw, the bigger the amplitude of this function. Now the arrow is not just going to stand still, it's actually going to rotate. It rotates counterclockwise in the xy plane, and the angular frequency of its rotation is omega. So omega in our function corresponds to how fast this arrow is rotating in the xy plane. The last thing to note about how this works is if we project that arrow onto the x-axis, that is what gives us the value of the function at any given time. So if we take a look at the example that I'm about to show you down here, the arrow starts off on the x-axis. So x is equal to a. That means the value of our function is equal to a. But then the arrow rotates a bit, and now it's on the y-axis, so x is equal to 0. Then it rotates some more. Now it's on the negative x-axis, so x is equal to minus a. Rotates even more. Now x is equal to 0 again when the arrow is on the y-axis. And then it goes back to its starting position where x is equal to a. Well, if we actually plot that out, again, we start at a value of a, we go to 0, then to negative a, then back to 0, then back to A, and then just repeat that because the arrow keeps spinning around, this is just a cosine function plotted out. Okay, so if we take a look at the animation now, again, as the arrow rotates, just keep track of the x-coordinate of the tip of the arrow. Okay, whatever the x-coordinate is, that is the value of our function f of t. So what we're doing is we're representing the behavior of this sinusoidal function by using a rotating arrow. And that's really what a phasor diagram is. A phasor is just that rotating arrow. Okay. And we can also use phasor diagrams to visualize how different sinusoidal functions add together. So for example, let's say we have f1 as a function of time, which equals a1 cosine omega t. And then we also have a second function, f2, which is equal to a2 cosine omega t plus theta. So the idea is these are two different sinusoidal functions with two different amplitudes, a1 and a2. Omega is the same for each function, so we're talking about the same frequency here. But the two functions are out of phase with one another, which is indicated by this angle theta in the second function. So if theta is equal to pi, then they're pi out of phase. If it's equal to pi over 2, then they're pi over 2 out of phase, and so on. So at any given moment, at any given value of t, we can actually add the two phasors together just like we would with vectors. Remember, with vectors, we have something called the tip-to-tail method of vector addition. We're basically going to take that same exact idea, and you probably learned this back in Physics 44 or an equivalent course, and we're going to apply this to phasors. So we're going to start by drawing the first phasor with a length a1. So when t is equal to 0, this phasor should be pointing straight to the right along the x-axis. And then we're going to show the second phasor added tip to tail with the first one. So we'll have a second arrow whose length is a2. And to show that it's out of phase with the first one, we have an angle theta between those two arrows. So again, if this is a 45-degree angle, then I put a 45-degree angle between the two arrows. So with those two arrows on the page, now we can see what the total is. The total amplitude when I add these two phasors together is shown here. And so this arrow goes from the tail of the first phasor to the tip of the last phasor. And we call the length of this A total for the total amplitude. We'll also notice that between the first phasor and the total phasor over here, there's a certain angle phi. So we have two things we might want to solve for: the total amplitude A total and that phase angle phi. And we can basically just work that out using what we know about geometry. In this case, we've constructed a triangle. So all I have to do is solve for this length of the triangle and this angle in the triangle. I've basically turned this problem into a geometry problem. And so once I've worked those out, the total function, f total, is equal to A total, the total amplitude, times cosine omega t plus this phase angle phi. Again, we can work out the total amplitude and the phase angle phi using geometry. So we can also use phasors to understand constructive and destructive interference of two waves. Remember that if we have two different waves that have the same frequency and the same amplitude, then they will constructively interfere as long as the phase difference between them is equal to 0 or 360 or 270 and so on. So here's what the phasor diagram would look like in that case. So here's the first wave represented by an arrow with length A. And here's the second wave. Again, it's an arrow of length A. And if there's 0 degrees phase difference between the two, then the first arrow is exactly in the same direction as the second arrow, and the net, or the total amplitude, is just equal to 2 times A. So we can see constructive interference is happening because the amplitude is bigger than that of the individual waves. Okay? If we also say that the phase difference between them is 360, Well, then I draw the first arrow, and then when I draw the second arrow, I spin it around 360 degrees, but guess what? It's still facing in the same direction, so it's still the case that the net amplitude is just 2 times A. On the other hand, destructive interference. If we have 2 waves of equal frequency and equal amplitude, but this time the phase difference between them is 180 or 540 or 900, then this is what it looks like. We draw the first arrow, and if the second arrow is 180 out of phase with it, then I need it to actually face in the opposite direction. And in this case, those 2 arrows will exactly cancel each other out. That's destructive interference. Okay, A net would be equal to 0 in this case. Or if we say the phase difference is 540, I draw the first arrow going to the right. Now the second arrow, I have to spin it around 540 degrees, but guess what? It's still facing to the left when I do that. So when I add these 2 phasors, I get 0, okay? So that's how we show constructive and destructive interference using phasor diagrams. And just to remind you, there's another way to visualize constructive interference. So here, we're actually going to draw the waveform. Okay. And then we'll draw a second waveform. And in this case, I'm showing the 2 waves exactly in phase. So if this is point P on the first wave, that exactly lines up with this point P on the second wave. So the phase difference between them is equal to 0. Now remember, this will also work if I take the first waveform, leave it as is, but then I shift the second waveform over by 360 degrees or 2 pi radians. So now here's that point P on the first waveform. Here it is on the second one. So the phase difference between the 2 waveforms, delta phi, is equal to 360 degrees or 2 pi radians. And we still have constructive interference because we have a peak which meets another peak, allowing the waves to constructively interfere. Now, we have destructive interference. Then we draw the first waveform like this. And we draw the second one 180 degrees out of phase with the first. So here's what that looks like. So if this is point P, denoting the first peak of the first waveform, that same peak is going to be found over here on the second waveform, shifted by an amount delta phi equals 180 degrees or pi radians. So this is just another equivalent way to think about it. Either you can just sort of visualize the 2 waveforms stacked on top of each other, or you can draw a phasor diagram. Either way, the underlying math that we're talking about is the same. These are just different ways of visualizing what's going on. So let's do an example. Let's construct a phasor diagram showing the addition of 5 waves, each with amplitude A and frequency omega. The phase difference between successive waves is 45 degrees. What is the amplitude of the resultant wave? And then as a follow-up, what is the phase difference between the first wave in your diagram and the resultant wave? Okay, so we have 5 different waves. Each one is 45 degrees out of phase with the last one. So this is the first wave that we have shown in blue. The next one shown in red is 45 degrees out of phase with that. The next one shown in green is 45 degrees out of phase with the red one, and so on, okay? So these are the waveforms that we're adding together. We're going to use a phasor diagram to see how they add together. Okay, so let's draw the phasor diagram. First, I'm going to draw a phasor pointing straight to the right. That will be my first one. Now, the fact that I have it going to the right is totally arbitrary. It doesn't actually matter which direction I show it going in, as long as the next phasor I draw is at 45 degrees relative to the first one. So here is a 45 degree angle between the first 2 phasors. The next one is at 45 degrees relative to the last phasor I drew. So it will be pointing now straight up like this. And then the next one is going to be at 45 degrees relative to that. So it's going to be pointing up and to the left slightly like this. And again, the length of it is A. And then finally, we have to have 5 in total. So the fifth one is actually going to end up pointing straight to the left like this at 45 degrees. So the total amplitude goes from the tail of the first phasor to the tip of the last phasor. So this A net or A total is a phasor that's pointing straight up like this. Now, just by looking at the diagram, we can tell that the total phasor is at an angle of 90 degrees to the first one. Okay, that's a right angle right there. Now, if we want to know what A total is equal to, what is the total amplitude? Well, we basically just have to add the vertical components. Of all the phasors that we drew, because the horizontal components are canceling out. We only get something that's pointing straight up at the end of this process. So the first phasor I drew has a vertical component of 0. It's pointing only horizontally. The next one is going to be amplitude A times sine of 45 degrees. We want this part right here, the vertical component. So that would be A times sine of 45 degrees. For the next phasor, this one over here, the vertical component is A because it's pointing straight up. And then for the next one, this one over here, it's once again going to be A sine 45 degrees. And then the final phasor is pointing to the left. It's only horizontal. There is no vertical component. So that's A total. So we have a factor of A we can pull out. Sine of 45 is root 2 over 2. Then we have just 1. And then sine of 45 again is root 2 over 2. So we have A times the quantity, root 2 over 2. I have 2 factors, so it's just root 2 plus 1. So it's approximately equal to, if we calculate that numerically, 2.41 times A. Okay, there's another way you can see this, by the way. We can basically ignore the first phasor and the last phasor because they cancel each other out. So I can circle right here. I have a phasor with the length of A pointing straight to the right. And then over here, I have a phasor with a length of A pointing straight to the left. These will cancel out, leaving us only with these 3 which have vertical components. Actually, if we go to the original graph, we can make some kind of sense of this. The first phasor cancels out with the last one. The first wave is this one here shown in blue. The last one is this one here shown in purple. Notice how they're 180 degrees out of phase with each other. Where I have a peak of the purple wave, I have a trough or a minimum of the blue wave. So those two cancel each other out. Again, that's another way of seeing that. Okay, so here's another one for you guys to think about. Construct a phasor diagram showing the addition of 4 different waves, each with an amplitude A and a frequency omega. The phase difference between the successive waves is 90 degrees. So we have 4 different waves like this. Each one is 90 degrees out of phase with the previous. The question is, what is the amplitude of the resultant wave? So pause the video, try to work this out by drawing a phasor diagram, then come back to it when you think you have your answer. Okay, so as before, we can draw the first phasor in any direction we like. Let's just have it going to the right like this. But the next one is at 90 degrees relative to the first phasor we drew, so it's going to be pointing straight up like this. and the next phasor is at 90 degrees relative to that. So it's pointing to the left. And then the fourth and last phasor is pointing at 90 degrees relative to this one. So it should be going straight down like this. So actually, the phasor diagram starts and ends at the same point. The net amplitude is supposed to go from the start of the first phasor we drew to the end of the last phasor we drew. But in this case, there's actually no distance between those. So A net is exactly equal to 0. Whenever your phasors form a closed loop, then you get 0 net amplitude. So let's do one more. Let's construct a phasor diagram showing the addition of 6 different waves, each with amplitude A and frequency omega. As before, the phase difference between successive waves is 90 degrees, but now we have 6 of them instead of 4. So what is the amplitude of the resultant wave? And then as a follow-up, what is the phase difference between the first wave in the phasor diagram and the resultant wave? So pause the video, try to work this out by drawing a phasor diagram, and see what you get, then come back to the video. Okay, so as usual, we're going to start by drawing the first phasor going straight to the right like this. The next one is at 90 degrees relative to the first phasor, so it's going to be going straight up like this. The next one is at 90 degrees to that, so it's going to be going straight to the left like this. The next one is at 90 degrees to that, so it's going straight down. So we have 4 waves so far. We need 6, so we have to actually keep going. So the next one is going straight to the right again. And the one after that is going straight up. Now we have 6 waves, each one 90 degrees out of phase with the last. That's the phasor diagram. So the net amplitude is going to go from this point down on the lower left of our diagram to this point on the upper right, because we started here at the lower left and we ended up here at the upper right. So our net amplitude goes across diagonally like this, okay? So let's actually simplify this a little bit, right? If we want to know what A net is, basically we have a triangle which cuts across the diagonal of this square for the side length A net. There's a right angle here, and then this side is A and this side is also A. Because those two sides are the same, these two angles here are also the same, and that would be 45 degrees. Because in order to get these to add up to 180, those angles both have to be equal to 45 degrees. So actually, we've answered one of the questions. Angle between A net and the first phasor is 45 degrees. It's the 45-degree angle we see right here in our diagram. So next, if we want to figure out what A net is actually equal to, we can use the Pythagorean theorem. So A net squared, being the hypotenuse, plus is equal to A squared plus A squared. So that's the Pythagorean theorem applied to the triangle we just drew here. So A net squared is equal to 2 times A squared. So A net is the square root of 2 times A squared. The square root of A squared is just A, so this is root 2 times A. Okay? That is the total amplitude when we add these waves together. It's root 2 times A. So hopefully you get a sense of how we draw phasor diagrams. In the next lecture video, we're going to be continuing on with this and drawing a lot more phasor diagrams. So we'll end this one here, and I'll see you in the next one. But as always, take care, be healthy out there, be safe. See you later.